For decades, experimental aircraft have followed a familiar script. Years of simulations, controlled ground tests, incremental hops into the air, each powered by fuel, batteries, or engines the world already understands. Then one test flight broke that pattern. No dramatic countdown, no roaring engines, just an aircraft rolling forward, quietly, before lifting into the sky and forcing everyone watching to ask the same question. What exactly is keeping it airborne? This was the moment Maxwell's experimental aircraft completed what would later be called a historic test flight. Not because of how high it flew, not because of how fast, but because of how differently it flew. From the start, this aircraft wasn't designed to impress crowds. It was built to answer a single, uncomfortable question: whether flight could be sustained without relying on traditional energy assumptions. Observers on the ground noticed something immediately. The takeoff was smooth. The climb was stable. No visible exhaust. No surge in power draw. No signs of strain. Engineers monitored telemetry in real time, watching parameters they expected to fluctuate remain remarkably steady. Voltage curves stayed flat. Thermal readings stayed within narrow margins. The aircraft behaved less like a prototype pushing its limits and more like a system operating exactly as intended. And that was unsettling, because experimental aircraft are supposed to struggle. They're supposed to reveal weaknesses. They're supposed to make engineers nervous. This one didn't. As the aircraft continued its flight, completing controlled turns and maintaining altitude, the test team shifted focus from whether it would fail to why it wasn't. The aircraft wasn't drawing power in bursts. It wasn't compensating aggressively. It wasn't behaving like a battery-powered platform conserving energy. It was steady. That steadiness changed the tone of the test entirely. What began as a cautious evaluation turned into a moment of quiet realization. This flight wasn't just validating an airframe, it was validating a concept. And when the aircraft touched down, smoothly, deliberately, the silence on the runway said more than applause ever could. Because everyone there understood something fundamental had just been demonstrated. Not a finished aircraft. Not a production-ready system. In the hours that followed, the focus shifted from the runway to the data. Engineers replayed telemetry frame by frame, searching for hidden compensations, unseen spikes, anything that might explain away what they had just witnessed. But the numbers told a consistent story. Power input remained stable. Energy output aligned with predictions. Control surfaces behaved within expected margins. There was no obvious trick. No sudden reserve being drained. No delayed cost hiding behind the success of the flight. And that's when the implications began to settle in. If this aircraft could sustain controlled flight without the familiar energy trade-offs, then endurance was no longer tied directly to fuel load or battery mass. The traditional equations that govern range, payload, and efficiency suddenly felt incomplete. Aviation has always been a discipline of compromise. More fuel means more weight. More batteries mean less payload. Every gain costs something else. But this test flight hinted at a system where that balance might be altered, not eliminated, but fundamentally restructured. Observers noted something else that hadn't been planned for. The aircraft's acoustic signature was unusually low. Without the roar of combustion or the strain of high-output electric motors, the aircraft moved through the air with a subdued presence. For surveillance, research, or long-duration monitoring, that detail alone carried enormous implications. As discussions unfolded, comparisons inevitably surfaced. Solar aircraft rely on daylight and weather. Battery aircraft are constrained by charge cycles and degradation. Hybrid systems still depend on fuel. This platform fit neatly into none of those categories, which made it difficult to classify and even harder to ignore. Within days, interest spread beyond the original test team. Aviation researchers requested briefings. Independent engineers asked for replication protocols. Analysts began modeling what such a system could mean for unmanned flight, cargo transport, and remote operations. Yet, despite the growing attention, the aircraft itself remained unchanged. No redesign. No dramatic upgrades. It simply existed, quietly proving that the assumptions governing flight might not be as fixed as once believed. And as preparations quietly began for longer-duration tests, one reality became increasingly clear. This historic test flight wasn't the destination. Beyond that doorway, the questions grew sharper and more uncomfortable. Because once flight is proven possible, the next question is endurance. Not minutes in the air, but hours. Not controlled paths, but sustained missions. Engineers began outlining scenarios the original test had never been designed to address. What happens after extended operation? How does the system behave under continuous load? How does it respond to turbulence, temperature shifts, or prolonged stress? And most importantly, does the stability observed in the first flight persist over time? To answer that, preparations for extended trials began quietly. No press releases. No public countdowns. Just methodical adjustments, additional instrumentation, and expanded safety margins. The goal wasn't spectacle. It was certainty. What stood out during these preparations was how little the core system needed to change. The airframe didn't require reinforcement. The energy system didn't need scaling just to stay aloft longer. Instead, the focus shifted to monitoring, capturing as much data as possible while letting the aircraft behave naturally. That alone raised eyebrows. Most experimental aircraft demand constant tuning between flights. Parameters are adjusted. Limits are tightened. Performance is coaxed forward inch by inch. This platform resisted that pattern. It didn't need to be pushed. It needed to be observed. And as engineers reviewed the growing dataset, another realization began to form. If this system could scale predictably, its impact wouldn't be limited to aviation. The principles demonstrated here, steady operation, low energy strain, minimal thermal stress, were transferable, not just to aircraft, but to drones, high-altitude platforms, and long-duration autonomous systems. The conversation widened. This wasn't just about how an aircraft flies. It was about how machines operate when energy stops being the primary constraint. Because when energy becomes stable rather than consumptive, design priorities shift. Weight matters differently. Endurance becomes a function of mechanics, not fuel. Missions once considered impractical suddenly become feasible. And that's when the most important shift occurred, not in the sky but in mindset. The test flight had proven that the aircraft could fly. The data was now suggesting something far more disruptive, that the rules guiding future aircraft design might need to be rewritten. And with longer flights on the horizon, the world was about to learn whether this historic test had revealed a curiosity. As those longer flights approached, anticipation grew, not from hype, but from uncertainty. Because aviation history is filled with moments where early promise faded under extended testing. Systems that performed flawlessly for minutes revealed hidden weaknesses after hours. Components that seemed efficient showed degradation. Margins that looked comfortable quietly disappeared. Everyone involved understood that risk. And yet, when the aircraft returned to the air for sustained trials, the behavior remained consistent. The same calm takeoff. The same stable climb. The same unremarkable, almost unsettling normality. Telemetry streamed in continuously. Engineers watched for drift, for decay, for any sign that the system was borrowing from some unseen reserve. But the patterns held. Energy input and output remained balanced. Thermal signatures stayed within predictable bands. Control authority never wavered. At that point, the conversation changed again. This was no longer about whether the aircraft could fly differently. It was about what flying differently meant for the future of aviation itself. Designers began sketching concepts unconstrained by fuel tanks or battery swaps. Long-endurance research platforms. Persistent environmental monitoring aircraft. Cargo systems optimized for reliability rather than range anxiety. Even emergency response aircraft capable of staying aloft when infrastructure below had failed. And then came the quiet realization that unsettled even seasoned experts. If this system scaled, the biggest limitation wouldn't be energy. It would be airspace policy, certification frameworks, regulatory definitions that had never imagined aircraft operating outside traditional energy models. In other words, the technology wasn't waiting for science to catch up. It was waiting for institutions to do so. That gap between capability and acceptance is where many breakthroughs stall. But this one had an advantage. It didn't demand immediate adoption. It could exist alongside conventional systems, proving itself incrementally flight by flight. And so the aircraft continued its work. Not loudly, not defiantly, just consistently. Each successful mission added weight, not to the airframe, but to the idea that aviation might be on the edge of a fundamental shift. That idea, interaction instead of consumption, became the quiet thread running through every subsequent discussion. Because aviation, at its core, has always been about overcoming limits. Lift versus weight, power versus drag, endurance versus payload. Every breakthrough in flight history has shifted one of those balances, but never removed the trade-offs entirely. Until now, energy was the immovable constraint. This aircraft suggested that energy might no longer be the dominant variable. It could become a background condition. Something stable, predictable, and no longer the primary focus of design. And once that possibility exists, everything else starts to change. Engineers began reconsidering airframe longevity. Without the stress cycles imposed by fuel burn or aggressive power draw, components could last longer. Maintenance schedules could stretch. Aircraft could spend more time in the air and less time on the ground. Mission planners began imagining persistence instead of range. Aircraft that didn't rush to complete tasks before energy ran out. Platforms that could loiter, observe, and adapt over time rather than operate on rigid timelines. Even safety discussions took a new turn. An aircraft that isn't racing against depletion behaves differently in emergencies. Decisions become calmer. Options expand. Margins grow. But perhaps the most profound shift happened quietly in how people spoke about the test flight itself. It stopped being described as experimental. It started being described as demonstrative. Not a prototype chasing viability, but a system showing what's possible. And that distinction matters. Because experimental flights ask if something can work. Demonstrative flights ask what happens next. As more data accumulated, as more flights concluded without incident, one thing became undeniable. This historic test flight had crossed a psychological threshold. Skepticism was no longer dismissive, it was curious. And curiosity, in science and engineering, is the beginning of change. The aircraft didn't announce a revolution. It didn't claim to replace everything that came before. It simply flew. And flew again. And with each quiet return to the runway, it carried with it a growing realization, one that the aviation world could no longer ignore. And that is where this story truly ends, not with a landing, but with a question. If an aircraft can fly without chasing fuel, if energy can become constant instead of scarce, if endurance replaces limitation, then what else have we been designing around a problem that no longer needs to exist? History shows us that every major leap in aviation didn't just improve flight, it reshaped the world beneath it. Longer ranges connected continents. Jet engines collapsed time. Autonomous systems removed human limits. This test flight belongs in that lineage, not because it was loud or dramatic, but because it was quiet, controlled, and repeatable. And repeatability is what turns experiments into industries. Whether this technology evolves, scales, or inspires entirely new approaches, one fact is already locked into history. A line was crossed during that flight. A line where energy stopped being the ceiling and started becoming the foundation. The sky didn't change that day. The aircraft didn't look different. But the rules did.